So, how do we add radicals? That is the main idea of this video. So if you haven't already learned what a radical is, I would definitely recommend going back and checking out the first 5.1 video I put out for this channel. But once you've done that, and if you have a sense of what radicals are and how to convert between mixed and entire, this is where you want to be. So a lot of this chapter focuses on doing just sort of like your basic operations with radicals, adding, subtracting, multiplying, dividing, whatever. So we're going to start with adding because it's, the easiest. So let's say I wanted to add 5 root 3 and 2 root 3. To kind of get the sense of how this works, let's just bring in something we've talked about in the past, if you're in my course, a dummy variable. And we're just going to replace those root 3's for a second, just really quickly, just to show how this works. So we're going to let x equal root 3 just really temporarily. If we do that, 5 root 3 and 2 root 3 are going to become just 5x and 2x. And this, you should definitely already know how to add, because this is something you've been doing since like grade 8. To combine like terms like this, we just remember add the coefficients. So 5x plus 2x is 7x. Keeping in mind, the x hasn't changed. And so if we backtrack here, well, x is just root 3. So really, this is just 7 root 3. And that immediately, hopefully, shows you how we add radicals. To add radicals, all we do is we just add the coefficients. And the radicand doesn't change. But just like adding polynomials, you can only add like terms, or, as we'd call them here, like radicals. So if they're not like radicals, and I'll explain what that means in a sec, there's nothing you can do. Or at least there's not much you can do. So to be like radicals, you need two things to be true. It has to be the same radicand. So here we were adding root 3 and root 3. And it also has to be the same index. So they're both square roots. And that's just like polynomials, right? You can't add an x and a y, and you can't add an x and an x squared. So there it was same variable, same exponent. Here it's same radicand, same index, but the process is pretty much the same. So if we want to add, say, 2 root 5 plus 11 root 5, all I have to do is 2 plus 11 gets me 13. The root 5's don't change, so it's just 13 root 5. Subtraction, same idea. So if I wanted to subtract, say, 2 times the 4th root of 7 minus 3 times the 4th root of 7, I'm just going to do 2 minus 3, which gets me negative 1, or just negative 4th root of 7, and done. So when you have like radicals, adding, subtracting, very easy, something you definitely already know how to do. But what if we don't? So there are going to be some cases where we can get around that. Let's say I ask you to do root 40 minus root 10. So first glance, the indexes are the same, right? So they're both square roots, but definitely not like radicals at the moment. So if the radicals don't match, or if the radicands don't match, there is one thing we can try to do, which is to simplify these to see if we can make the radicands match. And when I say simplify, what that means is turning them both into mixed radicals in the simplest form. So you want to try to pull out everything you can from both of these radicals. So this is kind of like working with fractions, where we want to try to get a common denominator before we add. The difference between this and fractions is that you can always get common denominators with fractions, right? You can always just multiply or divide to make it work. That's not going to be the case here. You can't always get like radicals. Sometimes you'll make it work, sometimes you won't. So if I've got root 40, thinking back to last time, we're going to do prime factorization. So we're going to break that down into a few 2's and a 5. I can make a pair of 2's in there. And so this is going to turn into 2 root 10. And so thankfully for us, we see, oh, hey, look, I do have a root 10. And so I am going to be able to make this work. So root 40 minus root 10 is going to become 2 root 10 minus root 10. And that's just 2 minus 1, so that just gets me 1 root 10, or just root 10. So let's try that with another one. I've got negative root 32 and 2 root 18. So definitely not like radicals, but at least the same index. So that root 32, I'm going to break up into a root 16 and a root 2. So if you watched my last video, you might have heard me mention that, hey, sometimes we can break our roots up into perfect squares. So in this case, I can recognize that 32 breaks down into a 16 and a 2, which is going to become just negative 4 root 2. And then same with the 18, I can say, oh, hey, 18 is going to break up into a 9 and a 2, which is going to get me 2 times 3 root 2, which leaves me with negative 4 root 2 plus 6 root 2. You could absolutely do that with prime factorization as well. So if that's the route you're taking, don't sweat it. It works just as well. And now negative 4 root 2 plus 6 root 2 is going to get me 2 root 2. And done. Problem solved. This also works with variables. So if you have root 9x minus root x, well, if we break down that root 9x, we're going to be able to pull out a 3. So that's going to become 3 root x minus root x. People do get a little bit confused once the variables are introduced. Remember, you're still just subtracting coefficients. This is just 3 minus 1, right? The x's aren't going to change at this point. So the 3 minus 1 gets me 2, and then I still have root x. All right. Try this next one on your own. It's going to be a fair bit harder because it's going to be a lot bigger, but see what you can make of it. So you're going to have 4x cube root 5x to the power 4 minus cube root 1080 x to the power of 7. So go ahead, break those down, pull out everything you can, combine, see where you end up with once you're done, and come back and take a look. All right, so the 4x is just a 4x, 5x to the power of 4. I'm not going to be able to take out anything with the 5, but x to the power of 4, right? So I can put 3 into 4 one time, so I can make one group of 3s in there. So I'm going to be able to pull out 1x, and it's going to leave an x behind. So this is going to be just 5x. The 1080 is going to break down into, a whole bunch of stuff. So that's going to be 3 2s, 3 3s, and a 5. And then x to the power of 7 is going to be 7x's. And all of that is in my cube root. So we got a group of 3 2s, a group of 3 3s, and 2 groups of 3x's. And so again, you could also just look at that x to the power of 7 and say, okay, well, 3 is going to go into 7 2 times, which gets me my 2 groups, and there's going to be 1 left over. So you wouldn't have to break down all of those x's individually. So what we're left with here is we've got 4x squared cube root 5x. And then on the other one, we're going to be able to pull out a 2 and a 3, which is going to get me 6. We're going to be able to pull out 2 x's, which is going to get me x squared. And then inside we still have cube root 5x. And so looking at this here, we've got 4x squared minus 6x squared, which is going to get me negative 2x squared, with the cube root 5x. All right, extending this a little bit and just adding more terms. So we've got 2 root 125 minus 2 cube root 5 plus 4 root 320 plus cube root 135. So once again, try this one for yourselves. I can say right now, one thing that should stand out to you is that we've got some that are cube roots and some that aren't. So you already know right from the get-go, the cube roots might combine, the square roots might combine, but the square roots and the cube roots are never going to combine. So go ahead, break this one down, see what you come up with. All right, so I'm going to skip the prime factorization step and just start pulling things out. So the 125, I am going to be able to pull out a 5, and it will leave 5 behind. The 2 cube root 5 is just going to stay as is. The 4 root 320, I am going to be able to pull out an 8 or pull out 3 2s, depending on how you do it, which is also going to leave behind a 5. And that 135, I'm going to be able to pull out a 3, which is going to leave me behind cube root 5. Try to keep in mind, chances are if I'm asking you to add, there's a good likelihood that things will combine together. So if you get a 5 here, you can kind of trust that you're probably going to get a 5 here as well. Not guaranteed, don't just assume. But when you're doing your prime factorization or you're doing whatever, keep an eye out for the numbers and see if you can get, like, if they end up matching up. If they don't, go back and double check to make sure you didn't mess something up. So when we simplify this, we end up with 10 root 5 minus 2 cube root 5 plus 32 root 5 plus 3 cube root 5. And so I can combine those 2 cube roots together because they're both cube roots 5s. And I can combine both those square roots together because they're both square roots 5s. So the 10 and the 32 gets me 42 root 5. And the negative 2 and the 3 just gets me cube root of 5. And yes, these both do have the same radicand, but one's a square root, one's a cube root, so they do not mix. And this is just where we leave it. We end up having 2 terms. All right, I'm going to give you one word problem to try here, just something to make this a little bit more challenging for you. So let's see what we've got. I'm going to draw you a couple of circles. So something that looks like this. And we're going to have a line that connects the middle of those 2 circles. Like so. I'll tell you the areas. So the area of the bigger circle, so I'm just going to call that area 1, is going to be 48 pi. The area of the smaller circle, which I'll call area 2, is going to be 12 pi. And so what I want to know is what is the length of the line? So how far apart are the middles of the 2 circles? But specifically, I want the exact distance. So that's something you're going to see a lot in this chapter, the word exact, which just means I want you to leave it as a root. I don't want you doing decimals. And again, you're probably not going to be allowed a calculator, so doing decimals would be pretty hard anyways. Before I get you to do this one on your own, I will just give you one helpful reminder. You're working with areas, right? I gave you areas for both circles. So remember, the area of a circle is pi r squared. So see what you can do with that and see if you can figure out how to get the lengths of your 2 circles here. Or sorry, the length of the distance between the centers of the 2 circles. Okay, so to answer this question, we need to know this distance and this distance, right? So the 2 lengths inside those circles. So if you don't remember, what those lengths are is your radii, the radius of each of the circles. So we want to find the radius of the bigger circle, radius 1, and the radius of the smaller circle, r2. So for our bigger circle, we've got a1 equals pi r1 squared. But we know what a1 is. That was given to us. That's just this. So if we take that 48 pi and we plug it into our formula here, we get 48 pi equals pi r squared. And we just want to solve this for r. And what we can do here is say, oh, hey, I've got pi on the right. I don't want that. So I'm actually going to divide both sides by pi. But the nice thing about what I gave you is that those pi's are just going to cancel out. And so we end up with r1 squared equals 48. Well, I don't want r1 squared. I just want r. So I'm going to square root both sides of that. And what we end up with is our radius 1 is just root 48. Our second circle is going to work exactly the same way, right? So it's going to end up as 12 pi instead of 48 pi, but that's still going to equal pi r2 squared, and the work's all going to be exactly the same, so I'm not going to show it again. We're going to end up with r2 equals root 12. To get that distance, the distance between the 2 circles, it's really just those 2 radii added together. So that's root 48 plus root 12. Well, if I'm going to add those, I need to make them like radicals if I can. So the root 48, once you break it down, is going to become 4 root 3. The 12 is going to become 2 root 3. And so if you add those together, we get 6 root 3. If I had given you a unit, like say I had said it was meters squared, we would definitely add a unit here, but we don't have one, so we're just going to leave it as 6 root 3. And there we go. That is the distance between our circles. And so that's adding and subtracting. It's not overly complicated. It's mostly just break them down, add the coefficients, away you go. So in the next video, we're going to start touching on some multiplying and dividing. So once you've got this one down, go ahead and move on to the next one.